So, do a quick summary of the previous episode. So, we are looking at a simple model of diffusion topological mechanics. So everything is linear in terms of the stress, relation between stress, strain, concentration, chemical potential, concentration, and strain. Okay, we also have a linear relation between the flux and the gradient of chemical potential. Okay. We want to solve the problem, so we need to solve conservation of mass and conservation of linear momentum. Okay, which is written. And so in the end, we want to solve this by numerical methods. Okay. So we are interested in deriving a weak form. Okay, so this we did last time, right? Okay, remind me because there are just too many classes at the moment. So we've done this, I think. So here, when we count things, we need, okay, we see that in this weak form, for example, okay, we have gradients of our non-concentration field or displacement field. We have first for the gradients of the virtual fields. This one. Okay, so all this is fine. But here we realize that we have here's the gradient of the displacement field, and then we need to take another differential operator. So if we had linear approximation, piecewise linear approximation of the displacement, like what we did in the 1D case, for example, okay. So in the 1D case, this would amount to a second derivative of the displacement. Okay. If you have piecewise linear approximation, you don't catch this. Okay. So you have a problem because your coupling term vanishes. Okay. So you would have to go at least to second order interpolation function, okay, which is feasible, of course, but it's and then okay, then you can ask, okay, do I also do second order for the concentration? And my model becomes bigger quite quickly. So, okay. Okay, so there is an alternative. Okay, so if we have, I go back here. Okay, I know that the chemical potential is given by this. Okay. Okay, so I can invert this if you want. I can write it. Okay. And for example, I can I'll try to put this into here. Okay, so C minus C0 is going to be a mu minus an epsilon over H. Okay. And we'll change the variable and work with chemical potential instead of working with concentration. Okay, so then if I do this, simply this H epsilon minus M C minus C0. Okay, this term which appears in the first equation. Okay, this becomes I've got M And then, okay, mu minus h. Okay, so I want to gather the terms in epsilon. Okay. I've got a sort of m squared, but okay, it's not a standard square, it's a product, a tensorial product of two second order tensor, which gives me a fourth order tensor. Okay. This I can write the fourth order tensor here. Then I've got this. Okay. There's one page. Okay. So this means, okay, here I've got, this is, okay, in terms of indices. And so I got my thing here, if I write it in terms of indices, okay, I've got something like h, I, j, k, l, epsilon, k, l, minus m, I, j, and then the thing is mu minus m, k, l, over h. So I rewrite it as okay, so this is an elasticity tensor. I could call this if you want. Remember in the Thomel part, we had exactly the same thing in the Thomel part. Remember we had the isothermal elastic modulus. Now our standard Young's modulus, for example, is the isothermal one, and we had an adiabatic elastic stiffness, which was different from the isothermal. Okay, so here we have the same thing. So this H is the elasticity at constant concentrations. Okay, so remind you that we also written sigma equal to h. This is the term which is there actually. This is the sigma. Okay. So h measures the change of stress when I change the strain, keeping your concentration constant. Okay. This one measures the variation of the stress. I change the deformation and I keep the chemical potential constant. Okay. So you can wonder if you are doing experiments, you can actually wonder which one you measure. Okay. Okay, so let's try to think for a moment. Okay, I've got porous media, for example. Let's take wet sand, okay, or soil saturated with water. Okay. I want to measure the elastic stiffness. How do I do this? How can I do this? What kind of experiments could I do? Do you have any idea? Yeah, exactly. Okay, so you put your sand in a little cylinder box, and then you push. You see how much you need to push to get the. Okay, so it's a bit more complicated than because okay, you get all the compressibility of the water and so on. So but fundamentally, okay, so in this case, if you just don't deform it too much, you could consider that the concentration remains constant. Okay, the volume does not change too much. Okay. And if your cylinder is hermetic, I mean just completely, so you keep the concentration constant, and then you change the strain. Okay, here's the axial strain. Okay. You can get a uniaxial stiffness at least in this sense. Okay. Now, of course, if you have if you make holes in your cylinder and you let water flow out and you push, it's going to be softer, right? Probably. I mean, intuitively, I think you can gather that if you put the compression, the water will flow out, and then the thing will be softer, and there will be more displacement for a given force. Okay. So why? Because in the second case, you are considering the chemical potential. This is a rough explanation, but this is really the idea. I mean, okay, so you let the concentration change because you have flow out, and you keep the chemical potential constant somehow, because okay, you change the strain, but you change the concentration at the same time, so that okay, so you have a negative strain if you compress. And this means normally, but the concentration does not increase. So it's not so clear, but okay, but fundamentally the idea is roughly to keep the chemical potential constant. Okay, so it's a way to explain that there are changes in stiffness according to what if you isolate the system in terms of concentration or chemical potential. Okay, so the idea would still be that the stiffness at constant chemical potential visibly is normally smaller than the stiffness at constant concentrations. Yeah. Okay. Okay, and then I can do this change of variable also in the second equation. Okay. You get a bit more developed. Okay, okay, just replace C everywhere by, so the C dot is going to become an epsilon dot and a mu dot. The grad C is going to become a grad mu and the grad of epsilon, but okay, this is going to vanish with this one actually. And in the end, you get something like this. Okay, so you have, in terms of mechanics, conservation of momentum, okay, it's just very similar to what we had before, except that, okay, we use this different stiffness tensor. Okay. Okay, so this is exactly what we do, right? And now, for the weak form of the mass conservation equation, yes, okay, you have a C dot, but the C dot is like mu dot over H, okay. This is your typical quadratic term in diffusion, okay. It's a mu, okay, okay. And then you have your coupling term now. There is an epsilon dot, but okay, at least you got rid of this extra spatial derivative. Okay. And so this looks, in practice, just like the thermal case, the thermoelastic case. Okay. If you say mu is equal to temperature, this, and okay, the coefficients are a bit different, but you can really, mathematically, it's the same problem as the thermoelastic case. And all those things we discussed about doing different solution scheme would apply to this. Okay. Okay, so it also means that, for example, if I want to solve them in a monolithic way, I can do it, no problem. If I want to do staggered schemes, okay, the isothermal scheme here would be isochemical potential scheme. Would freeze the chemical potential, solve for the mechanics, then get the strains, and then from the strain and strain rate, solve this in terms of chemical potential in the second stage, and go to the next step and so on. Okay, just like the thermoelastic case. But we've seen that this is only conditionally stable. I mean, you have the same kind of problems. Okay? Potentially the same kind of problems of numerical instabilities appearing if I do a staggered scheme. So, okay, so we should do maybe the equivalent of adiabatic, but okay, it's a different problem. So we can maybe later try to figure out what it means, but adiabatic scheme, but okay. Maybe it's better that you do the exercise on the thermal mechanics first to really gather really deeper what the staggered algorithm, staggered adiabatic scheme is. Okay. So that's what is said here. Yeah. Okay. Oops. Okay, if we look at it, I mean, we've seen already that in the thermoelastic case, we don't have symmetric matrices. Okay. Actually, what we can do, we're going to see this in a second. But okay. If you put a minus sign in front of all this, then okay, the matrices will become symmetric. Okay. Well, okay. But to put a minus sign, and then you have to work out how you handle the acceleration. But you could get something symmetric. But then, okay, it's going to be you're going to change the. So you're going to have a minus quadratic form here. So this itself, I mean, in terms of the big matrix, means there are blocks which are positive definite and blocks which are positive negative definite. We'll come back to this after. And there's a better way to see this, actually, by trying to formulate this as a variational principle. Okay. So remember, okay, we've seen minimum potential energy. It's a variational principle. You minimize the energy, and this gives you the balance equations. Okay, the solution is actually the one which minimizes the energy. Okay, so we do this also in this case. So we have discussed this a little bit. So let's come back for a moment. Okay, this is the slides which I added. You cannot print them because they are on Hippocampus now. And I did them yesterday in the train, so okay. I could not put them online before that. Okay. You have the result in the slide, but okay, here I've added the slides to show you the path to get there. Okay, so we start, okay, the basic model, diffusion. Okay, we're going to look at the steady state case. Okay, so we know concentration is constant in time. You have a steady state regime, maybe you inject things on one side and it comes out on the other side. In between, there is a distribution of concentrations which correspond to this flow of water in a clear sand or in soil. Okay, so I want to show. Okay, so we have already seen this. I can formulate this as a variation principle. Just just like I can do any elliptic problem, I can formulate this as a version. Okay, so if I remember correctly, I did this a few classes ago, but you can go back quickly because it's easy. So, okay. I define this this functional, because I've got a field mu. Okay. I take the gradient. I know the quantity, the diffusivity tensor. Okay. Compute this. If you remember, this is the function phi c of mu, of grad mu, which I gave you before. This is does not come from nowhere. I mean, it's remember. Yeah, we can go there. This is this one, okay? This is just this one. Okay? This is defined at every point. And I just integrate over the domain, okay? So if you look at it, these are the dimensions of a power. Okay. And I also, okay, here, okay. Just to simplify things, I've removed the source term. The RC, okay, I consider that there is no volumic source term. Everything is controlled by boundary conditions, okay? The common case. Okay, so the conditions are, I impose either, okay, for the moment I'm going to work with chemical potential, so I impose the chemical potential on some part of the boundary, and on the other part I impose some flux. Okay? Standard, really standard. Okay? I construct this functional. Okay, and this is going to be power because I've got a chemical potential times the flux. It's into some power. Okay. So okay, and okay, and this is on the next slide, but I say that the mu. So it's a stationary case. So basically depending on the there's no time in this for the moment. Okay. So this is the one which is which is minimizing this function. Okay. I minimize. Okay. You can put it that you want. And I just impose that the mu over which I minimize, or the mu's, are those which verify the Dirichlet boundary conditions. Okay. Okay. To verify these boundary conditions. So I can imagine all sorts of chemical potential fields. Okay. This way I think we have done it before. Okay, so remember how it works. Okay, we write, so we want perturbation. Okay. Imagine that mu is the minimum, the one which minimize, the minimizer. Okay. And create a small perturbation. Okay. And I want that. Okay. Okay, so if you want, I tried U tildes, which are perturbation of the minimizer. Okay, and I want there that the stationarity condition. Okay, we see that it's a quadratic function, so it's going to be convex. So the minimum is really clearly defined by stationarity condition. Okay. We've done this before. Okay. Of course, the delta mu's should be equal to 0. On that part of the boundary, because there I know what mu is. Okay, so I don't like with perturbations elsewhere. Okay. This is the standard derivation. We've done it before, I think. Pretty sure. Not at all? Okay, so okay. We discussed when I introduced the variation principles. Okay, and given things like this. Okay, so basically the difficulty here, I want to minimize a function which is itself a function of a function of in space. Okay, so maybe a bit conceptually difficult. So I'm doing this directional derivative. I want to transform this to as a minimization with respect to a scalar, because this I know how to do it. Okay, so I choose delta mu. And this is a function of epsilon. Okay, and I want this to be minimum and epsilon equals 0. Okay? And I have to, then I can vary the directions delta mu. And if I have the minimum, whichever direction I look at, if I'm the minimum at the bottom of a valley, whichever direction I look, it goes up. Or it's flat and then goes up. But locally it's flat. I mean, I cannot roll down. Okay, so this is what it says. Okay. So what? So it's a field of this. Okay. What is the? Okay, this one is simply. Okay, that's again. So if I replace in this, to the first term, I'm going to have a. Two mu's, but okay. The two terms which are in mu, so we directly write it like this. Okay, so this is a term with no epsilon. Okay, I have a term which is a mixed one. I've got square mu. Okay. And this one, and I have a term which is then I've got a term. So there is an epsilon in front of this. Another epsilon square here. Okay. So when I take the derivative with respect to epsilon and I set epsilon equal to 0, I get only the term in the big brackets. Okay. So this term in big brackets would be exactly what I'm looking for. This is going to be the d epsilon e epsilon delta mu. Evaluate the function equals 0. a constant, it will vanish when I take the derivative.
Is that delta j omega, the integral?
Yes, it's this one.
Oh, okay.
The part of the boundary where I impose it's part of the boundary where I impose the flux.
Mhm.
This one is the part of the boundary where I impose the contagion. Okay, so this should be equal to 0, whichever delta mu. Okay, here again I'm going to have a nice divergence theorem to do. Okay, so so this condition, okay, this becomes that, so in replace my integral, I do my divergence theorem, I've got the minus integral of omega divergence kappa grad mu times delta mu dv. I've got the integral of the boundary of kappa mu times n delta mu a and the plus okay. Okay, right, admissible, so you verify this condition. Okay, so that this condition says that it's 0 on this part of the boundary. So here, when I do my divergence, I've got 0 over the whole boundary. But in the end, everything which is mu, delta mu vanishes, so I'm only left with this one, okay? And okay, since this has to be 0 for any delta mu, I need to have this equal to 0, and the part which is the integral here also equal to 0. So it tells me that I can put the minus, it doesn't really matter here. And I must have also okay, but in the interior of the domain, the open set, we need to have this. So this integral is 0. And on the boundary, at least on the part of the boundary, delta j omega, we need to have this equal to 0. But okay, so this is the solution of our problem, because in this case, here I put the Cauchy model, so I know that minus kappa grad mu is the flux, okay? So this part is minus the flux. So I find divergence of the flux equal to 0. That's what I wanted. Okay. And this is also minus the flux. I've got it minus the flux times N plus Q bar equals 0, so this is exactly what I want to take. Okay, so doing this is the same as solving these equations. Okay? Again, this is the idea of the variational principle. This works for any, it's very well established in mathematicians for sure, but also in the heat, the stationary steady state heat equation is the same, going to be the same thing. If you have an equation which is divergence of something which is depending on the gradient, so it's basically in the end it's Laplacian of something equal to 0, then you can formulate it as a variational problem. It's just very standard. Okay. So this one is the easy part. Okay? I knew this. This was obvious. Okay. It is obvious to you now, not 1 hour ago, but now it is. Okay, if you have a heat transfer, is divergence of the heat flux equal to 0. The same kind of, this one can do the same thing. Elasticity, static elasticity is the same thing. You can apply this in the static electromagnetism, which will work as well. Darcy, we can put it in this one. Okay. Now, there's an interesting thing is that. So here, this corresponds to the the steady state. Okay, we want to do the transient in the end. Okay, so we started with the easy one. Steady state, it's quite clear. It has nice structure. It's a nice quadratic function. We minimize it. It works. No problem. Okay. So there is always in these things. There is always this notion of duality can work. Here with chemical potential, but okay, since it's steady state, it's mostly the gradient of chemical potential, which is important. Okay, the level of the chemical potential is controlled by the boundary condition. Okay. If you had no chemical boundary condition, your mu would be defined up to a certain constant. Okay. Now we can also work in the conjugate quantity mathematically. We can formulate things in terms of the flux directly. Because here we try to find the chemical potential field, which verified our equations. Okay, but our equation is this one. Okay, so we could try to directly find the flux. Okay, we can try to directly find the flux. Okay. And actually, again, this is pretty well established. There is another functional, which is dual to the first one. Okay. Which is done by this. So this one, I go back for a second. Okay, but this appears also in our. Is this one okay? In our thermodynamic description, this appears. So it's something which makes sense to somebody who's going to do quantitative modeling. Okay? Here in the very simple case, but the idea that you could generalize this later to more complicated cases. Okay? And now I have to take into account boundary conditions, but okay, so here I work on J, so the J I will know a few things about it on the boundary, on the Neumann part of the boundary, okay? But I don't know the flux on the Dirichlet part of the boundary. When I impose mu, I have no idea about J, so this way it's a no. So there will be a term appearing also here, okay? So it's the power of the unknown flux times the known chemical potential. Okay. Okay, but this is becoming a bit more complicated in this case.
Which part is the known flux? J there?
Okay. Okay, so just wait a second. So I'm defining this functional, so it's a scalar valued quantity which I can compute from a field of J. Okay? And J of X. I can compute this, I can compute this, and this is known, it's the imposed chemical potential on the part of the boundary. Okay? Now what I'm telling you is that the flux, which is a physical one, is the one which minimizes this functional, okay? Among all flux fields. But this is where it becomes a bit more complicated than before, because I need to impose restrictions. Okay? I cannot really take any flux fields. Of course, I want flux fields which verify this. This I was expecting this. Okay? On the part of the boundary, delta G omega, the flux is known, at least this normal component is known. The tangential, I don't know. I know the normal component. But here I also have to impose that I want a flux which is divergence free. I need to test fluxes which have zero divergence. Okay? Technically this is not so easy to do. There are ways to create functions which have zero divergence. Okay, if you make them a rotational of something, another field, it will work. But, if you make it a rotational of a scalar field, the divergence of the rotational of a field is always zero. Okay, there are ways to do this. Yes.
Why is it different than what we did before? Because we're also, I thought you were saying we don't know the flux, but.
Yeah, okay, so here I'm trying here, for example, okay, you mean comparing this and the next one, okay? Here, for example, okay, let's say I want to do this, solve this numerically. I'm going to take, okay, I've got a scalar field, mu. I'm going to take a piecewise linear interpolation, standard finite elements. Okay, I put the nodes which are on that part of the boundary. I'm going to constrain the chemical potential to be what I want. And I put this in. I've got my simple interpolation, it's easy. Okay? Here, I cannot do just the same. In the sense, I cannot take piecewise linear interpolation of a vectorial quantity. I could take, okay, gx, gy, gz, with linear interpolation, piecewise linear interpolation. Okay, but there is, if I do that, there are no guarantee that this is true. Okay? So I need to come up with a parameterization of the flux. It's a bit more sophisticated. Okay, and one way to do this would be to put nodal values of a scalar function. Okay. Interpolate piecewise linearly, interpolate this function, and then take the rotational of this, create a vector field from there. Okay. So of course, if I have piecewise linear interpolations, the rotation will become piecewise constant. Okay, but okay, technically, locally, it will have, or if I go to higher orders, at least, I can show that this is very far away. So it's approximate, okay, but there are ways to do this. I can also, okay, I'm not going to go into these details, but there are ways to construct fields which are divergence free. People doing electromagnetics, for example, absolutely need that. If you have incompressible fluid flows, you need to do that too. Because you need to impose a divergence of velocity is equal to 0. There are ways to do it. This is not the. I don't want to go to this technical part. Let's stay for the moment on the. Let's assume we have a way to construct vectorial fields which are divergence free. Okay. Then among all those, we know that the ones which minimize this phi star function do verify the balance equations. Okay, I'm going to do some next time. Okay, so this is also relatively well known. Okay, there are properties. Okay, I'm not going to demonstrate this, but so we've seen before. Okay, let's look at this. A function phi, any admissible chemical potential field will lead to a phi which is larger than the optimal phi. Okay? So if I put a minus sign, I can write this inequality. Okay? Minus phi evaluated with an arbitrary nu tilde will be lower than minus phi evaluated at the physical potential. Okay? It's one thing. On the other hand, if this is true, which we need to show, but if I take a J tilde, this will lead to a phi star which is larger than the optimal one evaluated at the optimal J, okay, the minimizer. Okay? So I can write the inequality which is there. Okay? Now, if mu and J are the ones which verify all the equations, I can show, again there are integration by parts that at the value of J and mu which verify all the equations, I can transform this phi star into minus phi of mu. Okay? If in there I write J as minus kappa grad mu, and I account for the fact that divergence of J is equal to 0, I can go back to the other one, okay? Okay, I'm not doing it. You have to believe me, but so, okay, this kind of thing is very useful to evaluate the quality of a numerical approximation. Okay? Say, okay, you would like to find the mu and the J. Okay? You have an idea of what the solution could be. You make an approximation, and you give a guess for the field J, for example, and maybe another guess for the field mu. Okay. So you can evaluate both functions. Okay. If they were the exact solution of the differential equation, this would be the same thing. Okay. But if there is a gap between these two, this means that you have an error, okay, and you can quantify the error, the approximation error you do, by measuring the gap between this and this. If I give you two fields, so, okay, this one has already a lot of information because this one is divergence free and verify these conditions. Okay? So it's a lot already, okay? Maybe you can build some. But okay, only this is not enough to find the solution, okay? Because you also need to write the fact that J is linked to the gradient of a chemical potential, okay? The J is the gradient of something. But okay, if you have a guess, okay? The same thing here, you can take a field mu, but you don't know that the divergence of its gradient will be 0. You don't know it, maybe? Okay. So this helps you to compute, to quantify the error you are making in the approximation. It's a bit of a side note, but okay. That's why these things are interesting. Okay, it's, can be useful in practice. This also works in elasticity. In elasticity, this would be the displacement, this would be the stress. You have similar things. Okay, so let's check that this is actually giving me the solution. Okay? So here I need to minimize phi star, but I have a constraint on J. Okay, so this is constraint minimization. If you go to any optimization book or anything, did you have any course of optimization in your curriculum at some point? No? I mean, even before the bachelor. Okay, so there are different. If you have to handle a constraint, there are different ways to do this. Okay? One way is to introduce what is called Lagrange multipliers. Okay, a very standard way to handle constraints. So here, okay, I want to minimize this. I'm going to create called the Lagrangian. Okay, Lagrange, this name is used for many different things. Okay. This guy did many things. So I'm going to introduce a field which is the Lagrange multiplier. Okay. So it's an unknown field, lambda. And I use it to multiply a constraint. So if my constraint is verified, this is going to be 0 everywhere. This is 0. Okay. This is my other constraint. If this is verified, or on this part of the boundary, this is 0, this term is 0. Okay. So if my constraints are verified, this is equal to my objective function, the one I want to minimize. Okay. If the constraints are not verified, I penalize if you want. Okay, I have not. Typically, I will have a lambda which is negative here. This is positive. So okay, I'm not going to do the mathematical theory behind it. But okay. And so now I have to optimize with respect to J and lambda, but I can optimize. It becomes a non-constraint minimization in the sense that I minimize with respect to J, but I can take any J, any flux. If they are not divergent free, I will pay the price here. Okay. And I have to optimize with respect to lambda. Okay. So there are mathematical theorems, okay, which I'm not going into. But okay. If I give a lambda, I choose a field lambda. So this becomes a function of J, yes, okay. I try to find the minimum of this function, I know this convex in J, okay. I minimize this with respect to J for a given lambda. So this is a function of lambda, okay. It's possible to show that because phi is a convex function of J, this will be a concave function of lambda. Okay, so that's why I can write a max or a sup, okay, supremo. Okay, well, fundamentally, this idea is simpler than that. Of course, okay. This idea of Lagrange multipliers. Okay. If I take the phi star lambda, okay. If I compute this quantity, okay. So this is d over epsilon. Okay, J is fixed for the moment. Okay, so this is the idea. Okay, if I write this, Okay. So this is the stationarity of my phi star lambda with respect to lambda. Okay. It's like the directional derivative of with respect to lambda. This will give you. Okay, let me do this. It's easy to get. I think I need to read it in the details, but I get something like this. Okay. There's a minus here. The minus is a bit arbitrary, but okay. We'll see why I put a minus here. Okay, so it's pretty clear that if I write the function is stationary with respect to lambda, this amounts to enforcing the divergence j is equal to 0, and that is equal to 0. So I'm enforcing my constraints, my conditions. Okay? So I will have to, so I want to make it stationary with respect to j, because I want to minimize with respect to j, and I want to make it stationary with respect to lambda, okay? But now I could relax the constraint on j. I can make, okay? I made the problem a bit more complicated in the sense that I have to minimize with respect to the two, but I got rid of the constraint. Okay? So it's easier. Okay, and what I'm telling you without demonstration is that this stationary point, this stationarity condition, actually is corresponds to a maximum, because you can show that in this case the result of minimizing with respect to j for a given lambda is a concave function of lambda. Okay? We don't use the fact that it's a maximum in practice, but we have written stats. Okay. Okay. Yes.
So is J bar the constraint here, or is it J with the
The
arrow?
J bar is the imposed flux. The constraint is the equality. Okay. The constraint. My constraints are. So a constraint in the sense of a relation I want to enforce. Okay. J is not arbitrary. It has to be divergence free everywhere. It has to be such that J times the outward normal is equal to a known value on the part, the well-defined part of the boundary. Okay?
So J bar is the known value.
Yeah, I mean, okay, this defines a part of the, it's a constraint in the sense of a supplementary equation that you need to verify. Okay? Okay? So, I define this Lagrangian functional, okay? I've seen here the stationarity with respect to lambda imposes, okay? So if this function is stationary with respect to lambda and j, okay? The stationarity with respect to lambda will enforce this to be equal to 0 on the domain. So the j will be as I want. Okay, so this will be equal to 0. And this has to be equal to 0 for x. Okay? The only way that this is equal to 0 for any delta lambda, I must have this. There's no other way. Okay? So okay, now let's write, okay, this notation, okay, I got to it's like a scalar product, so this is the same thing here. Okay. So now if I write the directional derivative of my phi star lambda now with respect to a variation of the flux, okay, so this is okay. Sometimes we can write like this too. So this quantity is a scalar, okay, because it's an integral in the end, okay. It can be formally seen as the product of an object with the perturbation, and this is a scalar, so this is a scalar product, okay. So this application of this operator on this, you can check this is a linear operator, but, so that's why you can write it like this. And this I can interpret this as a derivative of phi. Okay. So it's a matter of notations, but okay. Maybe it's easier with this, and I can insist on the definition of this. So this one now is just as before. So we now derive from J. Fixed lambda, okay? Okay, so let's do it once. Okay, after, okay, I'll just maybe go faster, but okay, you can try to do this. So again, the phi star lambda of J plus epsilon delta J. Okay, so I got so it's the same as the so let's see, let's write it. This one is we have let's call it this way. This. Okay. Remind you that the phi star of J is this one, okay? Okay. And I also have a Epsilon square. Okay. And plus the other terms. So the one with J is in here, and I have an epsilon. I should have written it here. Okay. Okay. This is for the okay. This is the beginning, and then I still have the other part. It's a bit longer because I got these things here. Okay. So actually, yes, I can put the lambda here actually, and then I've got terms in epsilon. I've got and I've got sorry, So J here. Okay, yes. No, so this was a new year. Okay, this times mu bar. Okay. Let's see. Okay, I'll let you do the development if you don't trust me. Okay, okay. Really, if you inject this into that, I mean, this will give you this. Okay, so maybe I went a bit fast. That's what I mean, but you can redo it behind. It's just replacing and dropping the whole thing. Okay, so this part comes from this one, and this one comes from the constraint, okay? So in particular, I put these two together. Let me see. No, it's all right. So I cannot put them together for the moment. Let's not do this. Okay. I'm going to do it. It works in another way. Here, sorry, this is the lambda here. I'm anticipating a bit going too fast. I'm going to show that lambda is equal to mu when this is the point. After. Okay, but I want to simplify this, okay? So, okay, but what I can say, just to, that this quantity is what I'm interested in, okay? That's what I want to set to 0, okay? So if I derive this with respect to epsilon, okay, this goes. All the terms in epsilon are give a constant, well, with respect to epsilon. And the square term here will be an epsilon, but I take it as epsilon equals 0, so this vanishes, okay? So in the end, what's in the, okay, I can keep the color. Okay, what is in there is actually going to be, I got this. It will be contributions will come from here. Okay, I need to remove this one because it has equals away. What's in there? All the terms which are in the box. Okay, I'm going to rewrite it on top, but.
So, can you explain like the difference between when we're doing the functional derivative of each of these? Because in the second one, we're writing phi lambda star of j plus epsilon delta j.
Okay, so.
And the first one, what are we?
Yeah, so I say that, okay, the optimum, okay, is characterized by stationarity of the phi star lambda with respect to both j and lambda, okay? Stationarity means that it's flat, okay, maybe going up or down, but okay, but it's flat. So when I change lambda at fixed j, I should not change the energy to the first order, okay? it's power, it's not an energy. I should not change the phi star. And the same way, when I change j, keeping lambda fixed, I should also not see any change in the phi star lambda to the first order. So normally there is here, there is a, this is equal to 0. Okay? So basically I've got a function of two arguments if you want, and I write that the derivative with the first argument is equal to 0, or the second argument here. The derivative with the first argument is 0, 2. So I'm just taking directional derivatives with respect to lambda and directional derivative with respect to j here. So my two unknowns. And j is a vector valued function, lambda is a scalar value function. But otherwise it's the same. Okay? So I need to compute this quantity and this thing. And so this, what I mean, okay, so in this case I show you that it's this. Here, I take derivative and I set h equal to 0. I'm only left with the terms which are in the, without the epsilon, in the box, the dashed contour there. Okay?
So in the first one, we're just skipping the step where we expand with the epsilon terms.
Okay, it's faster. I did it faster
Just
because it's linear
yeah.
in lambda, so this is trivial. It's simpler. It requires less steps. Okay. If you put lambda, if you replace lambda by lambda plus epsilon delta lambda, the lambda term is going to give you. Yeah, I didn't write it. This will give you this plus a term is in epsilon delta lambda, but this will be exactly this with delta epsilon delta lambda. Okay? So I went a bit faster, yes. But we are doing the same thing. Okay?
Finally, the circle term goes to 0.
Without the epsilon, without the epsilon, it's okay. But I'm going to rewrite it there, so you can see. And then we have a small integration by parts to do, and then we're done. Okay. So I say that I have an integral over the domain of j kappa delta j d j then I'm going to put all together the terms. Got a minus integral over omega of lambda divergence of delta j d. And I've got this boundary term. These boundary terms. Okay, let's start with this one. I'll pass on the Dirichlet boundary. This one is so that's where mu is known. So and I've got the part on the Neumann boundary. And that's where the Lagrange multiplier is defined. Okay. Technically, you could define two Lagrange multipliers because there are two constraints. Okay, again, I remind you that when we do integral over volumes, we do this on open sets, so without the boundary. And then we have a Lagrange multiplier on the boundary. So if you put those together, this defines a Lagrange multiplier field on the sort of closed set. I want this to be equal to 0. All delta j's. Okay. I don't really have conditions on delta j's outside of continuity, derivability, and so forth. Okay, since I have the divergence, I need this to exist, of course, and it has to be integrable and all that. Okay. So So I'm going to do an integration by parts, and I'm going to do this term, okay? Because I've got everything in delta j, so but here I have a divergence. I'm going to get rid of this one, okay? So this term is the minus here. It's equal to an integral of the domain of grad lambda delta j d, okay, minus an integral on the boundary of delta j times n times lambda e, okay? And again, I'm supposing that the lambda on the bulk and the lambda on the boundary are